All right, guys, this is PreCal 3.2.3. This is day 2, and we're going to be continuing our finding how we can find the area under a curve. So last time we did those left and right endpoint rectangles, and then we added those up to kind of get a good estimate of the area. Now those were always over or under, but we found that if we added more rectangles, I mean those a bunch of really small ones, we could get a better and better estimate. So we then noticed, well, we're just adding up a whole bunch of things which are just changing by a little bit more every single time. That's what summations are really good at. So let's go ahead and try and see, hey, can we use those summations to do this? So we're going to go back to problem number 114. So that was the problem where if I pull up my document camera, we had our graph. It's kind of like that. And then we start at 1, 2, 3. And then we did our left endpoint rectangles. To estimate the area between 1 and 3, right? So that's effectively what we're doing. The equation here was f of x is equal to x squared. Okay, so I'm going to say, well, how can we do this now? So we're going to label these x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. So that's what all of these are. Okay. So what I want to do is figure out, well, what I was really adding up, right? So I'm adding up a bunch of rectangles, which was the width times the height. Now my width was consistent. My width is always 0.5. So I had like 0.5 times 1 squared plus 0.5 times 1.5 squared plus 0.5 times 2 squared plus 0.5 times 2.5 squared, right? And that's effectively what I did. So I had my width times my height. So the height was the only thing here that really changed. So if we think back to when we first did these summations, we said, well, how can we get a summation that doesn't count by ones, but it counts by like halves or 0.2s or things like that? Well, here, my rate of change is a half. So that would be 0.5x, it's kind of like my slope, right? Plus wherever I'm going to start, which in this case is going to be 1. Okay, so this thing here, this little equation will get me from my summation to my interval notation, my subscript notation, sorry, of this x sub 0, x sub 1, x sub 2. It'll give me from here into the actual x value. So this takes me from x naughts to 1 and so forth, right? This is kind of what this thing does, right? Why that's important is because my summation has to count in whole numbers. So 0, 1, 2, 3, 4. Now what this does is it converts those whole numbers into the decimals that I actually need to be counting by. Okay. Now once I have those numbers, right, my 1, so this gives me 1, 1.5, 2, 2.5, 3. Those are the numbers that I'm actually going to be raising to the second power. So this is what I plug in to the actual function. Okay, so that goes in for x there. So my height is equal to that 0.5x plus 1 squared, because it's just this plugged into that. Now if this was a more complex thing, you'd plug this into whatever x's you had in your function here. So now for x naught, right, I plug in effectively 0 into this, right? So 0 times 0.5 is 0, plus 1 is 1. So then this whole thing becomes 1 to the second power that's this. If for x sub 1, I plug in 1, 1 times 0.5 is 0.5, 0.5 times 1 is 1.5, that's where that 1.5 to the second is. So that gives me all of my heights, and my width is always just 0.5. So how I find my area is my width times my height. And I do that for each one of these. But I can now count by these, right? So I want to do a summation of 0.5x plus 1 squared. Again, it's just this thing here, which is going to be my height. So this gives me all of my heights, and I'm going to be plugging in from x being 0 until 3, because I'm only doing the left end point, so I don't want to go to 4. So 0 to 3 is my 4 rectangles. It can kind of throw you off because 0 is your first term. So this will add up all of my heights. Now what I really could have done here, and I'll write it here so you can see it better, 0.5 times 1 squared plus 0.5 times 1.5 squared plus 0.5 times 2 squared plus 0.5 times 2.5 squared. I can leave it here and just put this extra height inside of this and add up all of those different heights too, right? But I can also just factor out this 0.5 and have it be 0.5 times 1 squared plus 1.5 squared plus 2 squared plus 2.5 squared, right? So this thing here, that's my summation, right? This gives me that thing. So then I just got to take this summation and multiply it by 0.5. Now again, I could put that 0.5 on the inside, so 0.5 times this whole thing here, and it would do the exact same thing. But just a little bit easier if you get in the habit of putting it there. You'll see people do both. One's not better or like worse. I just prefer this. This is typically how you're probably going to see me do it. So now that we have this as a summation, let's grab our calculator and see what we get. So I just do 0.5 times math, go to my summation. I want to do x from 0 to 3. And this is 0.5x plus 1 to the second power. Again, a thing you want to keep in mind is don't use the parentheses it gives you as the parentheses for 0.5x plus 1, because those ones that it defaults to putting there are whatever is inside of them is what you are going to do the summation of. If you put that, say, second power on the outside of the one that it gave you, it will then do the summation of the rest, take that sum, and then square it, which is not what we want to do. So hit enter, and hey, there's that 6.75 we wanted earlier. Awesome. Okay. Well, not a big deal because that wasn't very hard to do by hand, but again, what if we increase the number of rectangles here? Okay, so let's top back over to this. Right. So what if we want to do the right endpoint rectangles? Well, how could we change this? So let's try that one. Well, all I really need to do is use 1 through 4 as opposed to 0 through 3. So I could just change this to being x starts at 1, ends at 4. That works just fine. The other way that I could do it is I could relabel these as x0, x1, x2, x3, and have me always start at 0, and then I would use, well, 1.5 is my x sub 0, so I would have to put plus 1.5 here, and then we do the exact same thing. So just to kind of show that, if I just copy paste the same thing, but I change it to going from 1 to 4, I get that 10.75 that I was after. Now, The other way that I mentioned is, well, if I have it start at 1.5, insert point, insert 5. There we go. I get the exact same thing, right? So you can do it either way. Typically, it's a little bit faster just to kind of change the x's to going from 1 to like 4. But there we go. Now we have our left endpoints and our right endpoints. Not a whole lot of change there. So because I can just reuse the same thing just in a different way. Awesome. So let's take a look at number 120. Well, let's find the sum of problem 117. So that was the one where we broke it up into eighths. Okay. Let's take a look at how is that going to change our equation. So our width was no longer 0.5, right? Our width is now going to be 0.25, right? And then over here, we're now going to be counting by 0.25s. So then our equation that takes our knots into numbers is going to be 0.25x plus 1, because I'm now counting by 0.25s, not counting by 0.5s. And then I plug this in there. So my height is going to be 0.25x plus 1 squared. And I'm doing the exact same thing. I'm just going to count by a different number here as opposed to counting by the 0.5s. So then my summation would be 0.25 times the sum of 0.25x plus 1 squared. Now I go from x equals 0. Well then how many of these do I have? Well, if I broke it up into 8 rectangles starting at 0, I would go to my 7th one. So 0 to 7 is 8, right? Because again, we're not starting our count at 1, we're starting our count at 0. So that's why I want to go from 0 till 7, right? So let's see if that gives us the same thing as we got the last time. So over here, type that in. So I want 0.25 times the sum of x from 0 to 7 of 0.25x plus 1 raised to the second power. There's my 7.6875 that we got the last time, right? Awesome. So this goes pretty darn fast. Well, what if I wanted the right end points for it? Well, let's go ahead and change that. So I could go and do the same thing and make it go from 1 to 8. I forgot to change the 1. Didn't take. There we go. And there's the right end point for it, right? So I can do that fairly easily. Well, what if I wanted even smaller parts, right? All I'm really changing is the width, what I'm counting by, and then how many things I'm going to add, which on a calculator, I can make those as tiny as I want, not a big deal. All I got to do is hit the enter key. So that's effectively where we're going to start going more and more in the future here. All right, let's hop back over here. So how do you determine when an approximation is an overestimate or an underestimate of the actual area under the curve? So there's that rule of if it's decreasing, then a right end point is under and a left end point is over. If it's increasing, then a left end point's under and a right end point's over. That's nice, but in general, you can kind of look at it and say, well, there's gaps under it, or you're overestimating just by looking at it. So the key is that you want to know when you are doing what, so that you know kind of what the range is. Is it under this and over that, or vice versa? All right, so with that, we're feeling pretty good. Here is our homework for 323. We're going to do 122 through 129. So I will talk to you guys next time.